in order to take questions if you guys had any. So I'm going to go through those real quick to see if there was any points that you were confused by, and so we can go through that. So we had the Lewis dot structures, and then we did the Vesper shapes. The Vesper shapes came from the valence shell electron pair repulsion theory. So the repulsion of those electron domains created these three-dimensional shapes. But we also know from quantum mechanics that there's atomic orbitals for the electrons. So how do we get those shapes? And so some scientists in the past have come up with this idea, this theory of combining the local bond theory and the Vesper angles of maximum distance between those and trying to figure out how the atomic orbitals will give us those angles. Because if you think about it, the atomic orbitals are at 90 degrees. And so that doesn't give you a 109.5 degree angle. And so there's some questions about this in the ALEX. And so this is what happens when we make a bond is the orbitals come together and they overlap, they interact. And so you have, like for these two hydrogens, you have one electron in each orbital. They come together, they interact, and they can form a molecular orbital that goes over the whole molecule. And it has a bigger box for those two electrons, and so it has a lower energy. So. And how these orbitals overlap, that's how they bond. And so we have terminologies that go with this, a sigma bond and a pi bond. And then we have other kinds of bonds that we really don't know what to call, but this pure sigma and pure pi bonds are shown here. And the thing is, if you look at these, I want you to be able to recognize these. Notice here, this is the bonding axis. And you see here that the sigma bond, the overlap is right along that bonding axis. Okay? Whereas on a pi bond, this is still the bonding axis. But the interaction, the overlap is above and below. So that's the pi bonding. We call it side-on bonding with those p orbitals, and it's above and below the bonding axis. And there's a node that contains the bonding axis. Here, this node, notice these nodes break the bonding axis here. And here in a pi bond, the node contains the bonding axis. So that's a skill you need to know as a chemist, that how you have a pi or a sigma bonding interaction. Now, how do we get with these p orbitals? We can bond things at 90 degrees real easily. We can have orbital overlap at things that are 90 degrees from each other. But how do we get other kinds of things? These other angles, like the 120 degrees or the 109 degrees, these are other angles that it's not easy to figure out. So the way we do this is we take an S and mix it with a P, or mix an S and a P and a D, and come up with these other angles. So that's what we have. We call that hybridization of the orbitals. And so in this case, to make a linear molecule, we take a S and a P and mix those together. Mathematically, we combine them. And notice if I combine this blue region here with this red and blue region, the blue region expands and the red region shrinks. Okay? And so it's just mathematically, think of it like the red as being negative numbers and the blue being positive numbers. Okay? And so we're adding those together and we're canceling out some of those negative numbers, and we're coming up with this shape. And so they really should shade this one red and that one blue. And then at some other time later, this might be red and the other one blue. But we come up with these shapes that are two independent orbitals. So in this case, this orbital has the maximum of 2 electrons in it, right? And this one has a maximum of 2 electrons in it. Okay. And now we can put 2 electrons in this side, and we can put 2 electrons in this side. So we can bond with something on either side. So if we have A in the middle, we can have an X on this side and an X on this side, and they can interact with 2 things. just like our picture here. So whenever we see a linear arrangement around a central atom, we call that sp hybridization, because we've taken an s orbital and a p orbital and made these hybrids, and they're across from each other. And that's the angle at maximum distance, is 180 degrees for two things. You can get them opposite of each other. And so we'll go through this. And now if we have three things, we need three orbitals. And so we always start with the s orbital, the 2s or the 3s, whatever atom we're dealing with. We take that s orbital and combine it with a couple of p's to get three hybrids. So we take the s, the two p orbitals, and make three hybrids, and they're at 120 degrees from each other. And so after we make those hybrids, we can put 2 electrons in each of those. And they can bond to three things. And so that's how I get my AX3, which is shown in that picture up there. And that's where I get the 120 degrees for sp2 hybrids. Okay, if I have 4 things bonded together, then it's going to be an sp3, because we have the s and we have 3 p's, and so there's the 4 atomic orbitals that combine to make the hybrids. And so here's a picture of that. It's just not really easy to see, but they're trying to show this. This one is along the z-axis, but these others are off in different directions. If you want a good picture of a tetrahedron, we've been drawing this one like with the carbon and the hydrogen. We draw 2 bonds in the plane, and we draw the wedges and the dashes. But if you ever want to make a tetrahedral object at the house or whatever, it's the opposite corners of a cube. And so you could also draw a tetrahedron in a cube. So let's draw that. This was one of the reasons I got into chemistry, because my professor could draw cubes really well, and I could see the 3D nature of it. I'm not sure if I'm as good as that person. So the carbon is in the middle, and you've got a hydrogen on this corner and on the back corner, and then on this corner down here and on that corner. And in that case, you've got a tetrahedral molecule. So the opposite corners of a cube are a tetrahedron. Or you could go get a game dice that has 4 sides. So a D4 tetrahedral dice, you can see that very nicely. And we name these by the sides, the faces, and so it would be a D4. So that's going to be our a tetrahedral molecule. And those are our hybrid orbitals, and they're at 109.5 degrees. Any questions on the sp3? Probably the most common one, because all of your carbon atoms bonded to 4 things. If it's no double bonds, then it's tetrahedron on each carbon. Every carbon has a tetrahedral electronic structure. And then you have the atoms stuck on there. Okay, then we get into the more tricky ones. The trigonal bipyramid. We need 5 orbitals, and we've only got 3 p orbitals and an s orbital. And so we need to reach up and get some of those 3D orbitals. If we're in row 2, we need to stretch out and get the 3D orbitals. But most of these molecules are not row 2 molecules. They're row 3 molecules. So it might be like a sulfur or a phosphorus or chlorine or something like that. And so since they're in the 3 shell, they have access to those 3D orbitals. And so they can reach out there and get one of them and mix it in. So we have an S and 3 P's and a D to make our 5 orbitals, an S, 3 P's, and a D. So that makes 5 hybrid orbitals, and they go off in these different directions. So this is also a new term for you, this equatorial positions and the axial positions. So you think of like Earth, you have the equator that goes around the middle, and then you have the 2 poles. And so in this case, again, we make these hybrid orbitals, and we can put 2 electrons in each, so it can bond to 5 things. Okay. And here's some examples with sulfur and chlorine and all of that. So these sp3d hybrid orbitals, there's different angles that describe these. There are 120 degree angles around the equator. So these are all 120 right here. And then this angle right here is 90. And of course, pole to pole is 180. So it's all very good. All right, and lastly, the sixth one. We need to bring in 2 d orbitals for this one, and so we have an s, 3 p's, and then 2 d's. So there's our 6 atomic orbitals that are going to be mixing in to make the hybrids. And so this is an octahedral electronic structure. And again, each of these hybrid orbitals can contain 2 electrons, and so that's how they bond at all of these different angles. Now, hybridization is strongest in the smallest atoms. And so you see as we get up to tellurium, way down here on group 5, that's way down. That's an enormous atom. And so it's whatever it's bonding to, there's not a lot of repulsion between these 2 groups. And so they just resort to the p orbitals. There really isn't any hybridization here. So this would be a p orbital here, bonding to this atom here. And this would be a different p orbital here, bonding to this atom here. And so you really don't need hybridization if it's a really huge molecule like tellurium bonding to something. But you get into the smaller molecules, especially carbon and oxygen, this hybridization model is something that they've used to try to describe the bond angles and to preserve the quantum mechanics of those wave functions. Okay. Now we'll see from molecular orbital theory we can get these angles a different way, but this is the hybridization way of thinking about it. Okay, so we can practice by labeling these different hybridizations. So, if we're looking at this molecule here, if we look at this carbon, you should be able to see right away. And these are some easy questions for you on the homework, on the exam. So look at this carbon. I count up how many groups there are. 1, 2, 3. So I need an S and 2 P's, right? This adds up to 3. We just don't put the 1 by the S. Okay. And so it's sp2 hybridized. And this one is also sp2 hybridized. So you can look at the molecule, you don't have to, a lot of times they're not drawn accurately, right? This is telling you the number of bonds, but it's not telling you accurately the bond angle. But you look at that, you see it's got 3 electron domains, so it's sp2 hybridized. And this one has 4 electron domains. So this nitrogen, you just add up the electron domains around it. These lone pairs count as 1 electron domain because they're in 1 hybrid orbital sticking out the top. And so then that's sp3 hybridization. And then those will define the angles. So an sp2 angle is 120, sp2 120, sp3 109.5. So even in this molecule picture, it's drawn as a 90-degree angle, but that's just because it looks nice on a piece of paper. It's not really accurate. So you would look at that and you say, yeah, even though it's drawn as a 90-degree angle, it's really 109.5 because those 2 hydrogens would snap out of the plane of the paper and form those other angles. Let's practice on these, okay? So here, this selenium has 5 electron groups. So we need 5 atomic orbitals. So the S counts as 1, you have the 3 P's, and then you have the D. So there's your 5. The equatorial positions would have an initial guess of their angle as 120 degrees. And then the axial positions from those equatorial positions would be 90 degrees. And then this carbon has 4 electron domains, so it's sp3, and those would be 109.5. And this one is sp2, 3 electron domains, so it'll be 120. These are actually things I would test you on, okay? drawing the hybridization pictures with the orbitals. I'm not going to test you on the pictures of the orbitals, but I will test you on bond angles and hybridization. Okay, because that's the vocabulary that you're going to need if you go into organic and if you're talking to anybody about molecular structure and bond angles. So what questions do you have about these? Yes.
So it will, like, the question will like read like, what is the hybridization of carbon?
Yes, or this oxygen. Here's an oxygen on this molecule. What's its hybridization? And so then you would count up the domains and you would see there's 4 electron domains. Okay, let's draw those. So we have this, 1, 2, 3, 4. So there's 4 of those. The pairs count as 1 domain. And so that's SP what? 3, SP3. And so that would tell you what so this is SP3. And then this, how would I write this on a test maybe? I would say, what is the angle for COH? So this little letter B, the angle, A for angle, and then the 3 atoms, COH. Does everybody see how what I'm using for text? I'm saying this COH angle. So it's the angle right here. That's easier for me to write out in text on an exam, rather than trying to draw a lot of pictures and everything like that. I might have the molecule picture and then I have a bunch of questions about it. Well, in my questions, I got to write out in text what I'm asking about. So I would say, what's the ACOH or the COH angle? And then you have a lot of options, 90, 180, 120, 109.5, and that would be the one. So it would be 109.5 degrees. So that's how I would ask that. And over here, I would say, I might ask, what's the angle between the equatorial fluorines? And you got to, well, what the heck is equatorial? If you don't know your vocabulary. So you would say, okay, that's going to be 120. What's the angle from? Or I might have labels on here like A and B and C. What's the angle between FA and FC? And then you would have to look at the molecule and see. So 2 electrons between each pair of bonded atoms, that's local bond theory. 2 electrons as a lone pair, that also counts as an electron domain. We hybridize the sp and d orbitals to give those directional angles of maximum distance. And that's the valence shell electron pair repulsion theory. Okay. So that's the first lecture. Was there anything in this one that you need clarification on? The main thing is count up the domains, and that's SP, SP2, SP3, SP. There's no SP4, it's SP3D. You have to pull in a d orbital because you only have 3 p orbitals. And then SP3D2. So that's the maximum, 6 domains, SP3D2. So let's go to the next one. All right, so this is funny, but the molecular orbital. So we did all this theory, and the molecular orbital theory comes in and says none of that works. Okay, so don't be panicked by that. So what we've done in terms of making this bonding, we'll talk some more about sigma and pi bonding. But let's make this molecule ethylene or ethene, where you've got this ENE indicates there's a double bond somewhere in the molecule. Okay, and so we've taken the atomic orbitals. For the carbons, you have the S and the 3 Ps. We've hybridized 2 of those p orbitals in with the S's, and we come up with these 3 sp2 hybrids. There's still an unused p orbital up there. We used 2 of those p orbitals. There's a third that's still remaining, and those can interact. So that p orbital, the sp2 hybrids are there in the yellow, and then that p orbital is those side-on interacting p orbitals. Now they're shown as really small, right? So this picture really isn't to scale. These p orbitals, they can be quite big. And so they can interact with each other and form this interaction right there. So you see how now they're kind of smeared onto each other. And that's that pi bond that's shown in this molecule. So one of these bonds right here is the sigma bond. And the other bond that we draw here is the pi bond. So when we're drawing that double bond, you have a sigma bond, which is end on, and then you have the pi bond, which is side on. And so local bond theory, we think of this as being 2 electrons here, 2 electrons here around all the carbons. And then this pi bond is really more like a molecular orbital. It's an orbital that goes over the whole molecule, but we can describe it as having 2 electrons in that orbital. Okay. And they can combine in terms of molecular orbitals. What if these p orbitals are shaded differently? What if the top was blue and the bottom was red? Okay. To understand what's going on with these orbital shadings, we need to think about what these orbitals are indicating. So we're drawing 2 dots on there as if the 2 electrons are like particles running around in that space. Okay, and that may be an easy way to think about it. But what we really should be thinking about is that these orbitals are oscillations of the electron cloud. And so there are places where the electron cloud bulges and gets bigger, and there are places where it shrinks and gets smaller. Okay? And so that's what's really being shown by the color. Okay, it's and that wave function is the electron. Like it's behaving like a wave, which is the thing that really confuses people. There's not like a particle stuck on that wave or bouncing around inside that volume. The electron is described by that wave function. So the electron cloud is the electrons oscillating around the nucleus. They're not in discrete little particles orbiting the nucleus. They're oscillating like a violin string, but it's really 3-dimensional. It's not just a linear string like on a violin. Okay. And so then what if there was the right side was oscillating out of phase with the left? Let's just do s orbitals. So let's come to these 2 s orbitals. When they're in phase with each other, they can interact. Okay, and they oscillate together, and now the molecule has a bigger space for the electrons to oscillate, and they have 2 positive charges that they can spread out over, and there's no nodes. And so whenever you put water in a bigger box, what happens to the level of the water? It gets lower, doesn't it? Same with the electron energy. If I can put that electron energy in a bigger box, it drops. Nature likes low energy. A ball on a hill will roll down spontaneously. You give electrons in phase orbitals, they're going to spread out over the whole molecule. So that's the reason we call this molecular orbital theory. We're going from atomic orbitals that are on individual atoms and letting the electrons go over the whole molecule. Okay, so that's what's going on with molecular orbital theory. Now, if they're out of phase, then they don't get to really spread out. I mean, they spread out, but there's a lot more kinetic energy. The number of times you have these breaks in the electron cloud, these are called nodes. I'll say nodes increase the energy. And in fact, they can increase the energy so much that it wants to break the bond. And so we would call this bottom one bonding, and that top one, because the node is creating so much energy, it actually is breaking the bond. So we have this competition between bonding molecular orbitals and anti-bonding molecular orbitals. We can do the same thing with p orbitals. When they come in of the same color, they're expanding together, they're interacting, and they're making the bond stronger because the could think of this volume of this little oscillation as where the electron is on average. And so if it's between the two atoms, then it's drawing those positive particles together because the electrons are negative. Okay, and so this would be a bonding interaction where you see this matches right here, so that becomes this piece right there. And notice right here, this doesn't match. So there's a node. And so it breaks the bond. So these side-on interactions can also occur where you have the same shading here. This is bonding. And this has a node right here. So this creates this node right there, and it breaks the bond. So we indicate that with a star. And so we have this in Alex to go through and recognize these different types of interactions. So when we see this, these dark dots in the sketch are the nuclei. We look at this is very similar to a pi interaction. So what's the symbol for this molecular orbital? We would go in, we would write pi, and this is going to be bonding, and this is going to be lower. So again, it's going to be compared to the atomic orbitals, this is going to be lower because the electrons can go around in a bigger box, and so they have no nodes, and it's going to be lower. Whereas this one, again, this is got a node that breaks the bond. It's very similar to this antibonding orbital, sigma star. So antibonding, and it's going to be higher than the energy of the orbitals. Here they're coming in at this shape. This is going to be that pi star interaction right here. So we would call that pi star. It's got a node that breaks the bond, so it's antibonding, and it's going to be higher in energy compared to the atomic orbitals that are the 2p orbitals. Here we have a sigma interaction. Remember that the bonding axis is right here, and there's interaction in between those two atoms, and so that's sigma. It's going to be bonding, and it's going to be lower in energy than the 2s orbitals. I think this should say 2s. I just did a copy and paste on that table all the way around. And then here, this one is also a sigma. Even though it's p orbitals coming together, it's forming a sigma bond. So it's bonding, and it's going to be lower than the 2p orbitals that came together to make it. So does everybody these are all the shapes. We went through all of them. So I wanted to make sure I kept hitting refresh on Alex until I got all the shapes. And so we've gone through every one of the different shapes in this lecture of the different types of bonding that we have. Now, one of the experiments that we used to understand molecular orbital theory was the magnetic nature of the electron cloud. There's a nice picture of this in the book where it shows the substance in a little beaker, and you got a magnetic field, and you got a balance weighing that's weighing the pull that the magnetic field has on the molecules. So you can condense different molecules, gases, and so on in these test tubes, and if all the electrons are paired up, then the molecule can go in and out of the magnetic field with no drag, right? But if you have something like oxygen with unpaired electrons, you put that in a magnetic field, then those electrons all pair up with the magnetic field, and you try to pull it out of the magnetic field, and you can measure that force on a balance. So you can see that there's some magnetism to this molecule. Well, most of the magnetism that science was familiar with was ferromagnetism. It was the magnetism of the nucleus. So you had iron nuclei with nuclear spins, and those would line up with magnetic fields. They would line up with each other, and they would create a magnetic substance, okay? Gases like oxygen, there's no iron in that gas. So, and we know that oxygen in itself, like an oxygen atom, is not magnetic. So why is the oxygen molecule magnetic? Well, it's paramagnetic. It has this magnetic electron cloud, not magnetic nucleus. And so this is a way to understand something about the electron cloud, and it confirms that we have molecular orbital theory is the more accurate theory for the electron cloud. When you get to PChem, we'll learn about X-ray and ultraviolet photoelectron spectroscopy, and it also confirms molecular orbital theory. So if we have these atomic orbitals coming in to make molecular orbitals, we have some bonding and antibonding arrangements. We can calculate that bond order. So for the bond order for hydrogen, is these two electrons in the bonding order, energy level, and you subtract the antibonding. And it takes 2 electrons to make a bond, so you take the bonding minus the antibonding, and so you're kind of looking at the balance. So if you have more bonding electrons than antibonding, then you have a stronger bond. In this case, we have 2 in the bonding, 0 in the antibonding, so we have a bond order of 1. Here's oxygen. So this is the molecular orbital diagram for oxygen. We have all of the atomic orbitals over here, 6 valence electrons. Down below, you have the 1s orbitals with 2 electrons in it. So there's all 8 electrons for oxygen. But the 1s orbitals do not interact. Now, if you ever come across that in ALEX, where it's interacting or bonding and antibonding on the 1s electrons on a group 2 or group 3 diatomic, let me know, because that's a mistake and I need to tell them that that's not valid. Okay, but anyway, it's only the valence electrons that bond. The 2 s's can form bonds, the 2 p's and so on can form these bonds, and we just went through all of the pictures of all of these different orbital pictures. And you can see here, as we add up our 12 electrons for 12 valence electrons, 2, 4, 6, 8, 10, 12. We have these unpaired electrons because of Hund's rule. So when we're putting electrons in, we fill in those horizontal or degenerate energy levels unpaired first, because each electron wants its own orbital when they're coming in. They repel each other. So if we've got 2 options that have the same energy, one electron's going to take that chair and the other one's going to take the other one, and then we're going to have to pair them up. Okay. So that's Hund's rule. And so that means that this electron cloud has unpaired electrons and it's paramagnetic. So we get to draw some of these in ALEX. So you can grab the boxes and drag them over here and put them in whatever space you want. And then you have the little label maker, and you can make the different labels, making subscripts and superscripts. And so you can practice doing those in ALEX. And then we have, looking at these MO diagrams, it says complete the table below and answer the question. So we have diamagnetic and paramagnetic, whether it's stable or not. And so here for carbon, we have 4 valence electrons in each carbon, so we have a total of 8. And so we can start putting those in: 2, 4, 5, 6, 7, 8. So everything's all paired up, so it's diamagnetic. We can calculate the bond order. So this is the 6 right here. That's the 6, and this is the 2. 6 minus 2 is 4, divided by 2 is 2, so the bond order is 2, and that means this is a stable molecule. So we would have an unstable molecule if we got a bond order of 0. So if we keep adding electrons to this molecule, so let's make C2 2 minus. So we can make anions on this and cations. So if I make T2 minus on C2, what have I done? I've added 2 more electrons. So we would put 2 more electrons here, that's actually making it stronger. C2 2 minus is going to have a triple bond because it's going to have 8 bonding electrons. But then if we go to 4 minus, we would have this. 6 minus, we'd have this. 8 minus, we'd have this. And once we get to C2 8 minus, we have a bond order of 0, and it falls apart. Okay, but we could, at least in theory, make a C2 6 minus, and it would be isoelectronic with fluorine. Okay, it would have a single bond. It would have lots of antibonding electrons, but it would still have 2 more bonding electrons than antibonding. Okay, let's do O2. Now this is going to be the MO diagram on the right. Okay, notice these 2 switch places. With the smallest atoms, lithium through nitrogen, this sigma bond is above the pi bonds, but for oxygen on up, they swap places. And so we're going to do oxygen on the right. We've got 6 electrons on each oxygen. So they come together, you have 12 total for the molecule. So 2, 4, 6, 7, 8, 9, 10, 11, 12. So the unpaired electrons means it's paramagnetic. Okay, we can add up the bond order. So this is the 8 right here. Those are all the bonding ones. And then the starred ones, those are the antibonding. So there's only 4 of those. 8 minus 4, 4 divided by 2 is 2. So we got a bond order of 2. And that's a stable molecule because the bond order is not 0. All right, let's do nitrogen. So nitrogen's here on the left. Each of them has 5 electrons. They come in and make 10 for the molecule. So 2, 4, 5, 6, 7, 8, 9, 10. Okay, everything's paired up. So that means it's diamagnetic. And then we have 8 bonding and 2 antibonding. So I'm just going to draw the 2 antibonding here. Everything else is bonding. So these 2 right here are the 2 antibonding. So that 8 minus 2 is 6, divided by 2 is 3, so it's a bond order of 3, triple bond. And yeah, it's a very stable molecule. All right. What if we did nitrogen plus? So now we've got, instead of 10 electrons, we have 9. And so we've just lost one of those electrons. Just pull one out, and now we have a cation. So N2 plus has 1 unpaired electron. It would be weakly paramagnetic. And the bond order, now we have 7 bonding minus 2 antibonding. So here's your 2 antibonding right here. Okay, that's 5. 5 divided by 2 is 2.5. So it would be like in between a double bond and a triple bond. It would be intermediate in bond length, and we can discover that that's the truth. It would be 2.5 bond order. Still a stable molecule, though. Let's do He 2 plus. Now it doesn't matter which side we use because it's going to be the same either one. So He, you see over there, helium comes in with 2 electrons each. So we have 4 total. So 2, 4. Everything's put together. I mean, everything's paired up. So it's diamagnetic. The bond order is the trick here. We got 2 bonding and 2 antibonding. Do the difference, we get 0. So we have a bond order of 0. And this one we're going to have to put no in terms of a stable molecule. So that's why in nature, helium runs around as a monatomic gas. It's not H2, like you have F2, O2, N2, Cl2, Br2. All of those are stable diatomics because of their molecular orbital diagram. But you get to the noble gases, and you have as many electrons in the antibonding orbitals as you have in the bonding orbitals. So local bond theory says each bond has 2 electrons assigned to it, and it's useful for creating the shapes in the molecular structure. So we're going to keep that theory for our molecular structure. But molecular orbital theory says the atomic orbitals combine and spread over the whole molecule, and this one has more experimental support. So anytime we're talking about the structure of the electron cloud, we want to talk about molecular orbital theory. So the hybridization orbitals, which again, it's somewhat useful in talking about the bond angles. And so we'll learn it, sp2, sp3, those kinds of things, and the bond angles. But those sp hybrid orbitals, they don't exist. Yeah. Okay. Something else has given us those angles. Okay. And whether it's the repulsion of the nuclei or just the interactions of those molecular orbitals, but it is a real handy shortcut. And it is a shortcut. You guys are real easy. It's real easy for you to draw Lewis dot structures, or it should be. You're working on it, but you draw your electron domains and get everything as far apart as possible, and you know those angles, and those are good angles. And we can talk about the hybridization giving those angles. But when we look at the electron cloud with paramagnetism or X-ray or UV light and pull the electrons out of those orbitals, we see the molecular orbital diagram. We see the energies of the molecular orbitals, and those are not hybrid orbitals, they're molecular orbitals. So molecular orbitals for the electron cloud, which is the reactivity of the whole molecule, that has experimental support. The angles that we get from local bond theory, they're good. They're good initial guesses. I mean, the molecule is going to change a little bit. Water's not going to be 109.5. It's going to move slightly, but that's a good initial guess. And so we'll learn that theory, but it will apply it only to the bond angles in the molecule. And we'll leave the electron cloud to molecular orbital theory. Okay, the course evaluations are open. So go to Blackboard sometime today and go. It's on the institutional page. So it's just before you get to the individual classes. You'll say start evaluation, and you can go in and you can pick your classes. It's really important to do evaluations for the courses. I read all your comments, and I make the course better. So we take them seriously, and the comments are the best. So take your time to put some constructive feedback in the course. If I did something well, tell me. If I could make something better, tell me. So it's going to be good. All right. So y'all have a good Thanksgiving holiday.